Welcome to a lesson with Dr. Powell. Let's look at an example of how we can use a definite integral. Suppose, for instance, that we have like a spring or an object or something that's going up and down, back and forth, and it's following this velocity function right here. When we have a positive output for this velocity function, that means we have speed going upward. When we have a negative, that means we have speed going downward. That's why we call it velocity. It's speed with direction. So what if we want to know what the change of position is between two different time periods, what the total displacement is? That means change of position. So let's suppose, so we want to know what the change of position is as t goes from maybe from pi 4 seconds to pi third seconds. All right, how much have we moved and in what direction? So to do this, we would compute the change. So basically what we want to do is find the change of the antiderivative of this from here, and we can do that with a definite integral. So we can compute here definite integral of sine t dt, and we're looking at the change as we go from pi fourths up to pi thirds. Now on a graph, look underneath the graph of velocity, this is how much we've changed. We take pi fourths and pi thirds, and we're finding this area right here. The change of area is also the change of the displacement, or the change of which is the antiderivative of velocity, because velocity is the rate of change of position. So if you take position, its derivative is velocity. So the antiderivative of velocity is position. The change in position is equal to an area, which we can interpret as a definite integral, which we can compute. We take any antiderivative at all right here of sine t. It doesn't matter which one, and we don't have to solve for c in particular at all. So this is true no matter how. So what we're about to compute will be true no matter what our starting position is at all. We don't need to know that because we don't need to know a plus c or anything. That information could be used to find a specific plus c for a specific antiderivative. But what if all we know is the velocity function and we don't know the position function at all? Then we can use a definite integral in order to compute this change of position, or which is also sometimes called displacement. How much it's changed places, perhaps. Okay, so we take an antiderivative, doesn't matter which one. Negative cosine t would work. We can check the derivative of this is that. And then we plug in our points, pi fourths and pi thirds. So plug them in here and we get negative cosine of pi thirds minus a negative cosine of pi fourths. So cosine of pi thirds is a half, so that's negative a half. This becomes a plus right here, and cosine of pi fourths is root 2 over 2. So it looks like our total displacement is root 2 minus 1 all divided by 2. This is a positive number, so it looks like we're going up in that interval, which should make sense because sine is positive right there. Now let's look at a case. Well, let's maybe when we might have a negative displacement. Why don't we start from pi, and let's go all the way to let's go to 2 pi even. So on this interval right here, this time interval, what is the displacement of the object when we have this particular velocity, sine t? How much has it changed? Again, it's kind of cool. We don't need to know where we're starting, but we can still know the change of position if we just know what the velocity function is via this definite integral. We compute. And let's see, negative cosine of 2 pi. And we have minus negative cosine pi. Compute this right here is, let's see, that's a plus, so it becomes a -1. This right here is a -1, so you end up getting -2. So this means that if sine t is our velocity function, then from pi to 2 pi, we've actually dropped a total of 2. In fact, you can kind of see what's happening here in particular. What we did is we computed the net area from here to here, which was -2. And from here to here, by symmetry, will be +2. So wherever our position is, as we go this way, our derivative or our velocity is positive, meaning we're going upward. And it looks like, how far are we going to go upward? We're going to go an upward of total of 2 units. And suppose, if this is t is in seconds, and maybe our velocity is in feet per second, so we've gone up 2 feet. Then what happens? Then it looks like we go back down 2 feet. So go up 2, then we go back down 2, and it's going to, process is going to continue by periodicity. Go up 2, down 2, up 2, down 2, up 2, down 2. So we have this back and forth pattern as we go. Thanks for watching.